In our series of problems, in this video you have 5 problems, and all of you go through each and every problem first and try to solve yourself, and after that go through the solution. Okay, cross check your answer with the given options. In this problem, important question it is on heating water, bubbles being formed at the bottom of the vessel detach and rise. Take the bubbles to be spherical of radius capital R and making a circular contact of radius small r with the bottom of the vessel, and the radius of contact circle is very less than that of the radius of the bubble, and the surface tension of water is given as capital T, and what is the value of small r just before bubbles detach, density of water given as rho w. Here we will see options. Let x is given as r square, then a b c d options are there, root 2 by 3x, x by root 6, and these things. Okay, solve the problem and compare with the options. You have to get option A as the correct one, that is root 2 by 3 r square root rho w g by t, and root is there for t also. Okay, so let us see here what they are asking in the problem. When temperature is raised, bubbles will move in upward direction, so they will detach at the bottom. Initially they are in contact, and here with the with the surface, see, this is the bottom surface, and if you take the bubble, the contact, this is contact, this contact region forms a circle here, that circle, whatever the thing is, circular figure is given in the diagram is that. Okay, so its radius is r. Let us take that this radius is small r. Okay, or total diameter given as 2r, that is the radius of that small circle is r. And let me draw a little bigger diagram. So this is circle in contact. Okay, so at this point, if you draw a straight line, the tangent at the point of contact, and this is the direction of surface tension, similarly here, and it makes an angle theta, or it makes an angle theta, and from here to here it is radius small r, radius of that circle small r, this is small r, right? And this circle, this bubble, whatever the bubble given in the diagram, this is the radius capital R. Okay, so when it is theta, obviously this also theta, and up to here we should draw, because this is the point of contact we took, this is the radius, up to here also radius. Okay, so here what is small r value, or opposite side means sin theta, you can draw sin theta is equal to opposite by hypotenuse, small r by capital R. So this is about diagram. Let us see the concept here involved, surface tension concept. See, same, surface tension is acting as shown there in the figure. If you resolve into components, this is one vertical component and this one is horizontal component. Similarly, all horizontal components, because here also surface tension acts in the same, if you draw a tangent, that is the direction of surface tension. If you resolve into components, this is vertical component and this is horizontal. All horizontal components are cancelled each other. And what is the vertical component? This is theta. Here this value is theta. So this becomes T sin theta. So this T sin theta surface tension is acting. So here the total force due to surface tension, let me write Ft, is acting vertically downward, and it should be equal to the force due to buoyant force, upthrust, minimum condition. Then only the bubbles will move in upward direction. They detach from the surface and will move in upward direction. So this is the basic concept. What is the buoyant force formula? Rho into Vg. Rho is the density of that liquid, or here water. And what is the surface tension? Force due to surface tension is, in this case, that circle is 2 pi r, total circumference 2 pi r, and value acting, the component is t into sin theta. Okay, so let us solve that equation. T into sin theta 2 pi r is equal to rho v is 4 by 3 pi r cube, capital R, volume of, and sin theta in the diagram we written as small r by capital R, that is also we substitute. T into small r by capital R into 2 pi r is equal to rho by 3 pi r cube into G into density of water. Whatever the things you can cancel it, finally calculate R. Now let us see second problem in this series, in this video. Here two parallel plate capacitors are taken, and C is connected to a battery and it is charged to a potential difference V. Another capacitor is 2C capacitance and it is also charged to a potential difference of 2V. And after that, the charging battery is then disconnected and the capacitors are connected in parallel in such a way that the positive terminal of one battery is connected to negative. If it take it as positive, and it will be negative plate. This is negative plate, this is positive plate. In that way it is connected, and they are asking to find out what is the energy lost in the final circuit if it contains only capacitor and only two capacitors, no batteries connected. It's a simple thing. Here pause the video and try to solve the problem. Here options are x, say x is equal to cv square, then 3 by 2 x, 3x, 9 by 2 x is 0. Now we'll see here individually they are charging, and after charging to V potential, the first capacitor is connected to V, charged to V potential, and second is charged to 2V potential individually. After that they are connected and this key is closed. Then what is the energy lost? Simple. Let us see concept first. If you take any capacitor of capacitance C, and if it is charged to a potential V, then the charge stored is C into V. And what is the energy stored here? The energy stored is of CV square. In terms of Q also can write if you want. Similarly 2C also. So another important thing is, you remember, that is total charge uh, total charge before and after should be same. Okay, total charge is constant. And loss of energy you can calculate by calculating initial energy, electrostatic potential energy stored minus the final one. Another concept in this you have to remember is, because capacitors are connected in series, capacitors are connected in parallel, the net capacitance is C1 plus C2, parallel combination. To which polarity? In this problem, positive polarity is connected to negative polarity. If it has Q1 charge, if it has Q2 charge, then here whenever you take the charge Okay, so that is also very important. This is the basic concept in this. Let us solve the problem. So here, first let us take first capacitor, individual capacitor of capacitance C, charged to a potential difference V. Therefore, in this case, charge Q1 is equal to CV, and how much energy is stored between the plates of the capacitor is of CV square. Similarly, take the another capacitor, because they are charging it individually, it has 2C capacitance and it is charged to a potential difference of 2V. Therefore, total charge on that is 2C into 2V, 4CV. And how much energy is stored here? Of the value we get is 4CV square. Therefore, now total initial energy how much? Of CV square plus 4CV square. Let us take as given in the case x, CV square as x. Okay, then this becomes 4x. Therefore, total initial energy becomes of x plus 4x. This is 9 by 2x. They are connected. These two are connected in the circuit such that their polarities are connected in opposite direction, plus to minus. So here the charge flow takes place. Okay, say charge is flown from plus C to 2C. You can take 2C to C. It doesn't matter. Charge flow takes place. Finally, the system attains to a final common voltage. Okay, because they are connected in parallel, the voltage across any capacitor C and 2C is same, VC. Now let us calculate what is the charge here. I write it as Q1 dash. What is Q1 dash here? How much it is? C into VC. And what is Q2 dash? Again it is 2C. Right here. Therefore, final the energy, potential energy is of CV square. C is the net value. How much? 2C plus C, 3C into VC square. Okay. So now let us apply conservation of charge here. Now we will see here conservation of charge. Initial charge is Q1 plus Q2 should be equal to the final value Q1 dash plus Q2 dash. So Q1 is how much? CV plus Q2 is how much? 4CV, and Q1 dash is how much? C into VC plus this is 2C VC. And here very important point is, while writing Q1 plus Q2, that is okay, CV plus, because it is connected to negative term, positive plate is connected to negative plate. Instead of taking place here, take minus. Charge is that minus constant. CV minus 4CV is equal to CVC plus 2CV. And if you cancel, this is minus 3 and this is 3 get cancelled. Finally, magnitude if you consider VC equal to V, minus will be there, but consider only magnitude, because negative is the case of direction. So how much voltage? Now they are at V voltage. Therefore, what is the final energy? Final energy also will write UF is equal to of 3CV square. Here, from here I am writing of 3CV square. Already X is taken as CV square. Okay, of 3 by 2 X. Now simple, just what is the loss of energy is initial energy minus final energy. What is initial energy? 9 by 2x. What is the final energy? 3 by 2x. You will get 6 by 2x, that is 3x. So answer is 3 CV square. So this is the loss in energy. Answer is B. Sorry, not A. Answer is B. Right. So here another problem. Photoelectric surface is illuminated successively by monochromatic light of wavelength lambda and 2 lambda. And if the maximum kinetic energy of the emitted photoelectrons in the second case is 3 times that in the first case, then the threshold wavelength for the surface is. This is the problem, interesting problem. Here you can pause the video, try to solve it. Very important and easy concept. Now we'll see the concept, photoelectric concept. So when alkali metal surface is illuminated, for example, take irradiated with a photon, say the photon energy is what? H nu, and in terms of wavelengths, if you write, it is Sc by lambda. So when this frequency is sufficient, that is greater than equal to threshold frequency, then electrons will be emitted out. They move with some velocity or some kinetic energy. Okay, so some kinetic energy K, or in this I write it as K. Law of conservation of energy, the incident energy H nu is equal to the energy required to remove the electron from the metal surface, called work function phi naught. This phi naught value equation we can write as H nu naught. In terms of wavelength, if you write, you can write as Hc by lambda naught plus kinetic energy. Okay, so kinetic energy of mv square, and if potential difference, stopping potential is given, ev naught also you can write. So wherever depending on the information given, that you can write, right? So this is the basic information. Let us now we'll see the equation. We'll solve the problem. So here, according to given data, E1 is equal to phi naught plus K1. So E1 is Hc by lambda, and this is equal to Hc by lambda naught. Let us write K1 as K1 only, and E2 is phi naught plus K2, and but E2 value, if you consider, E2 is how much? It is the wave incident wavelength is lambda by 2. So Hc by lambda divided by 2 means 2 Hc by lambda equal to phi naught, plus K2 is thrice of K1, 3 K1. That means what? 2 Hc by lambda is E1. Total thing you can write here. 2 into Hc by lambda naught plus K1 is equal to phi naught plus 3 K1. So what we get here, this is also, you can substitute Hc by lambda naught, and 2 Hc by lambda naught minus Hc by lambda naught, that is phi naught. I am writing this side. This is 3 K1 minus 2 K1, that is K1. Again K1 you can substitute. Again this K1 is how much from here? E1, that is Hc by lambda minus Hc by lambda naught. So from here Hc we can cancel. See, this is 2 Hc by lambda naught minus Hc by lambda naught is Hc by lambda naught. This is equal to Hc by lambda minus Hc by lambda naught. So Hc we can cancel. If you write Hc by lambda naught this side, it becomes 2. So 2 by lambda naught is equal to 1 by lambda, and they are asking lambda naught threshold wavelength. This is equal to 2 lambda. Okay.